Hey folks, welcome back to another video. Today we are looking at question 802, find eventual save states. Basically the question that's being asked here is that try to find nodes that are not involved in any kind of cyclic graph. So that's a problem that we'll be starting. And the way we'll be approaching this problem is by keeping a track of the number of nodes that actually have incoming into it. So for example, we know that 0 goes out to 1 and 2, but how many nodes are actually going to 0? So we know that that's that's why we need to create like a new array list that will keep a track of how many nodes are actually coming in instead of going out. And the other thing that we need to keep a track of is the incoming edges. So how many so how many times do things actually go out from it? So when we calculate that area, only 5 and 6 don't have anything going out of it, so they would have a degree 0 and 0. So once we have this, we'll use like a queue mechanism to be able to solve that problem. So let's jump right in. The first thing that we need is let's just get the length of the array. Graph.length. The next thing we need is a list of lists. And the reason why we need list of lists is to be able to store this data. So let's create that. And let's call it incoming nodes. It's a new array list. Right, and then what else do we have? Right, so we need a list of integers that we need to return. New array list. Okay, what else? I think that should be good for setup. Oh, we also need the degrees. So degree would be equal to new int of size n. Awesome. So once we have initialized the data structure that we care about, let's actually start storing this data. So before we do that, let's actually add the number of internal lists. So that can be done with a simple for loop. Let's do that. And then it would just be incoming nodes dot add new array list. Right, so that basically takes care of it. The next for loop, what we do is we actually create these two data structures and put data in them. So for int I equals 0, I less than n, I plus plus. So for int let's call it neighbors in graph of I. Yeah. So basically, once we have that, you would say incoming nodes dot get neighbor dot add 1. So what exactly is happening here? If we look at an example, we look at 1 and 2 for 0, and then we say for 1 add 0, and for 2 add 0. So this is like the final structure, but when we start off initially, this is where it's added. It's added here and here. And basically what it's saying is that at node 1, we have an incoming edge from 0, and at node 2 as well, we have an incoming edge from 0. Awesome. And the other thing that we need to do is increment the number of degrees. So for 0, the number of degrees that we have, you just increment it. So you take a look at basically for all of the neighbors, you're just incrementing the number of degrees. So in this case, we know that there are 2 outgoing edges. So you would put 2 for 0. here we have 2, we also put 2, you have 1 here, 1 here. So basically just like corresponding numbers. So the number of elements that it goes out. And the reason why we need this will become very clear in the following part of the code. The next thing that we need is we need a queue. And this queue basically goes over the number of safe states, and it keeps going in a loop, like a while loop, till the queue is not empty. Because once we know that 5 and 6, that's pretty obvious from the diagram, but there are other nodes that also are safe. So to be able to do that, we need to use like a while loop that checks whether a queue is empty or not. So let's initialize that queue. Would be new linked list. Right. So before we actually start the while loop, so what exactly does this need? So it needs to know what are the safe states, right? Even without any kind of computation, what are the safe states? And we know the safe states by the number of degrees, right? So 5 and 6 don't have anything going out of them. So how do we know that? So for int, we know that because we have kept a track of how many edges are going out of a particular node. Since 5 and 6 are safe, you add them to the queue. So you do for int I equals 0, basically iterating through all of them again. N I plus plus, you basically do, so if a degree of I is equal to 0, you do q dot offer I. So basically what you're doing is that, hey, like we've gone through the list initially. These are the 2 nodes that don't have any outgoing edges out of them. Therefore, we will add that to the queue. And once we have that, we'll have the while loop that actually goes through everything. So while q dot is not empty, pty int current would be equal to new q dot poll, right? And then once we have int q dot poll, what we'll do is I will actually iterate through all of the all of its neighbors, but we also need some sort of a data structure to know whether a particular node is safe or not. So the way we can go about doing that is, let's say we create like a Boolean array, safe nodes node is equal to new Boolean of size n. Awesome. So for so once you're pulling out of it, so we know that we're no longer we'll look at that particular node's neighbors, but we won't care about it again. But since everything that is in the queue is of terminal state, you will mark that as safe. So safe nodes dot current is equal to true, and we can use this data structure to return the result. So we have said, okay, so this node has 0 outgoing edges. So so basically we'll add that as a safe node. However, we need to consider the nodes from which this is also coming in. So for int, let's say neighbor in incoming nodes of current. So basically, since we have marked these nodes as safe, you will say that anything that is going into that given node, you can subtract the incoming degree by 1, right? So the degree of neighbor, you'll just subtract it by 1. So what exactly is happening? So let's look at an example here, right? So here we have 0 and 0. We know these are the terminal nodes. And then because they are the terminal nodes, we've added 5 and 6 into it. So once we have processed that, we look at 5 and 6. So 6 has nothing, so we don't really care about it. So we look at 2 and 4. So since we know that 5 is a terminal node, anything that goes into it, that can be subtracted by 1, because okay, we have eliminated that node. So basically 2 and 4, then when they are going into 5, we don't care about it. So we subtract the degree by 1. So we subtract this by 1 and we subtract this by 1. Right? And once we have this, we iterate through the queue again and we see if it is 0. If it is 0, that means this also has reached terminal state. And then we queue up 2 and 4. And then we look at 2, right? So all of the edges that are going into 2 are 0 and 1. So you subtract the degree by 1 for 0 and 1. And for 4, we don't really have anything. So we don't do anything. But in this case, right, we don't have any terminal states. So in the sense, like all of the degrees for the nodes right now are greater than 0. So we don't really care about that. So after we have subtracted it, if degree of neighbor is equal to 0, you add that to the queue. Queue dot offer neighbor. Awesome. So once that is done, that will just keep looping till the queue is empty. And in the end, it's pretty simple. So you basically need to loop through all of the Boolean array. So we could have actually done it in another way where we just count the degrees equal to 0 and add that as a result, which could have saved space. But now that we have initialized it, let's just go for that. So it would be res dot no. So it would be if Boolean of I, no, what's the name of the, control. If it is safe, if we have marked it as safe, then we add res.add is equal to I. And once that is done, you just return the result. Did I initialize that? Yes, okay. Awesome, so let's try compiling this. Of course, oh, right. Okay, let's try that again. Let me just format that. Classic. Okay, why doesn't it tell me before compiling? Incoming nodes, why I couldn't find symbol. Maybe that's a spell error again. Oh, right, incoming nodes.get, of course. Okay. So the first few test cases are okay. Everything else is okay as well. Awesome. So let's start with the space and the time complexity. The time complexity of the entire solution is of n, and n here would, like, if we look at it, we are basically iterating through all of the nodes and the number of edges as well. But it is still linear time because the number of edges are also in linear time, so it would be of n. The space complexity is also of n, since we are using like 2 new data structures, actually 3 of them, actually 4. So since we are using this to store the number of nodes that are incoming, the result that we store, the number of degrees that are going out, and what else? And this as well, the safe nodes. Awesome. So because of which, space complexity is also of n. Yeah, so that's the solution. If you have any questions, please let me know in the comments below. Don't forget to subscribe to the channel and like the video. I really appreciate that. It definitely keeps me motivated to make more videos. Thanks so much, and I'll see you folks soon. Peace.